Good morning, students. Today we will be continue the next concept, that is electric flux. In the last class we discussed the electric field lines and its properties and all. Now we will be go to the discussion of electric flux. Electric flux here. So electric flux in the sense, suppose if you take electric lines of force, so these are the electric field lines here. So in these electric field lines, if you are assume a surface, if you held a surface in the electric field lines, here I am taking the surface, here I am taking the surface here, same size of surface. If you observe here, through this surface, normally 1, 2, 3, 4 lines are passing, electric field lines, but the same surface if you taken here 2 number of electric field lines only passing through it. Then here the number of field lines are more, here the number of field lines passing through the surface normally is less. So we can say here flux is more, here flux is less. Flux in the sense, you can define like this. If a surface is held in a electric field, then the number of electric field lines passing normal through the surface is called as the electric flux. You can say like this. If a surface is held in if a surface is held in electric field, so we can say that the total number of electric field lines, the total number of electric field lines crossing the surface in a direction normal to it. The number of electric field lines crossing the surface normal to it. So this is the total number of electric field lines crossing the surface normal to it is called as the electric flux. Now here we have to define, before going to details of this electric flux, we have to define one more thing, that is area vector. So what is area vector? In mechanics in first year you studied that area as a scalar, but in this field case, in the magnetic field as well as electric field, in such cases we will be discuss the area as a vector quantity. Suppose if you, vector means its magnitude and direction. How can you know? Here is, suppose if you take a surface like this, and here if you take, this is the area A, and there is a small part you took here. The small part is dA, the small part area is dA. Then its direction of this vector dA is normal to its surface, so this is the dA bar direction. dA bar vector direction it is. We can also this has a normal vector, otherwise this is, you can represent with a unit vector n cap, then this unit vector n cap, then dA bar you can write as a dA n cap. So area is a vector quantity and its direction is normal to its surface. So area is a vector quantity and its direction is normal to it. Now we can go for the cases of electric flux. Suppose if you have a uniform electric field. We discussed already what is the meaning of uniform electric field. If the field lines are equally spaced and everywhere electric field intensity remains same, such kind of field is called as the uniform electric field. In uniform electric field, if you take a surface, and if the surface if you kept perpendicular to it, so perpendicular to the field, then what is the number of field lines passing through it, as well as if it is kept parallel to the electric field lines, what is the number of electric field lines passing through it, neither perpendicular nor parallel, by making an angle theta with it, how it is done. Based on the equations of those, we can generalize one expression for electric flux. So electric flux means you have to remember that it is the total number of electric field lines passing through a given surface when the surface is held in the electric field. Now, if a plane surface is placed in uniform electric field, if a plane surface is placed in a uniform electric field. Let us take a uniform electric field of intensity is E. This is a uniform electric field of intensity is E. Here, if a surface is held like this, if a surface is placed in this way, a plane surface is placed in this way, means perpendicular to the electric field intensity E direction, then here the area, this is having area, then area vector is, we discussed that is normal to the surface, then here area vector A bar and electric field intensity vector like this, and this area is A. If you taken magnitude of area is A, the electric flux in such case is the electric flux in such cases, we can take it as a phi is equal to EA. Here the electric flux will represent it with phi. In this case, we first you remember, then we'll make it generalize how it is. Here flux is nothing but, for an experimentally, it is phi equal to EA. When you got it EA in the sense when the surface is placed perpendicular to it, surface is placed perpendicular, but area vector is parallel to what electric field direction, then flux phi equal to EA we have. This is equation 1. Suppose if the what is the case here, we placed first one, if plane is what perpendicular to field. So here we taken a uniform electric field. In that first what we placed, a surface, plane surface is held perpendicular to the field. That time what is the expression we have is phi equal to EA. Next, if you taken that second case, if you plane is parallel to the electric field, if the plane is parallel to the electric field, second case, if the plane is parallel to electric field, see if it is plane is parallel to the electric field, you taken that uniform electric field like this, then if the plane is parallel to it, in the sense we can write like this, here the plane surface is parallel to it. The plane is parallel now in this case, but area vector is perpendicular. Okay, if the plane is perpendicular, area vector parallel. If plane is parallel, area vector is perpendicular. Why? Because area vector is perpendicular to the surface. Okay, so and the direction of electric field intensity is in this direction. Now angle theta here 90 degrees area vector, and then but when it is parallel to the electric field, then what happened here? No flux, means no this across the surface no electric field lines are passing. Okay, when it is kept parallel like this, when it is the field lines are passing like this, if you place anything, the maximum field lines will cross through it. But if you place like this, field lines are going from like this, if you place like that, this surface will not encloses any field lines. So same thing here we take, the field lines are going like this. Now we place it perpendicularly, then maximum field lines are passing phi equal to EA. But if you place it parallel, in this case no flux passing through the surface, no. So number of no flux here passing, no flux in the sense that is the number of field lines passing. Okay, so flux, no flux is passing through, no flux is passing through plane. Then we can say phi equal to 0. Okay, this is second one. So if the plane is parallel, electric field is 0. But if the plane is neither parallel nor perpendicular, so if the plane is neither parallel nor perpendicular, then at this time what is happened is the electric field lines are passing like this. If the surface is held, if the plane surface is placed in this direction, now to this surface area vector is normal to it. This is A bar, and this is the electric field direction E bar, and in between these two angle is theta. Then at this time what is happening here is the number of the flux, means the electric flux through this surface is the electric flux. So if you taken that electric field vector normal to the surface, electric field vector if you taken normal to the surface, what happens, that is E cos theta. Therefore number of electric field lines passing through it normally means that is flux equal to, we can write as a, here flux equal to E cos theta into A, that is otherwise you can write phi equal to, because if we resolve this electric field intensity along this direction, that's why here A cos theta. So you observe when it is the surface is perpendicular, that is the angle between the electric field intensity and electric field intensity and area vector flux is EA, and if the angle between the electric field intensity and area vector 90, flux is 0. If angle between electric field intensity and the area vector is theta, means flux is EA cos theta. So from this we can conclude that the electric flux through the surface is nothing but we can write as a, so these results can be written as, from these results, this you take as a 3, from these results, so we can write electric flux is a scalar product of electric field intensity E and area vector. Therefore flux phi equal to, we can write as a E bar dot A bar, or else phi equal to EA cos theta. So this is electric field, electric flux we can say. Electric flux is a scalar quantity because it is a dot product of electric field intensity and area vector. So electric flux is a electric flux phi is a scalar quantity. And what about the units? We can write as a units in SI, you can write in SI. So flux phi in the sense we know it is EA. Electric field intensity is the force per unit charge, means Newton per coulomb. Electric field intensity is Newton per coulomb, and area in the sense meter square. So the units are Newton meter square per coulomb. So this is what we can say as a electric flux SI units. Next we can go for, if the field, electric field uniform case, we can take like that. Generally a scalar product of E bar dot A bar. But electric field is non-uniform, or else the surface is not plane. it is a curved surface. In such case, means either the electric field is non-uniform or else the surface is curved. We have to be follow integral expression here. If the case we are writing, if the electric field is non-uniform, okay, or surface is curved. So electric field is non-uniform or our surface is curved. In such case, what will be discussed here is, if we take, in both cases we will take same thing, but I am using this method. What is surface is curved I am taking here now, okay. So surface is curved I am taking. For both of them you can use the same formula only, but I am using surface is curved, okay. Now I am taking uniform electric field only, but in uniform electric field what I am going to take a surface is curved surface. Like this uniform magnetic field is there, like this curved surface we have. When this curved surface is there, then we have to be, we have to make it into a small parts, okay. So this is, you have to make it into a small parts. Then in this you take a small surface area. This entire surface area is yes, let it be, but in this we take as a small surface area like this. The surface area vector is normal to it, so the surface area vector is, will take as a normal to it. This surface area is not complete surface area, we are taking a part of it. That's why its vector is, let it be, ds bar. And electric field direction, how it is there, this is the electric field direction, then angle between them is theta. Then flux, according to the flux, what we are taking, flux is nothing but what, scalar product of electric field intensity and area vector. So flux through the small area, the flux through small area, we can write as a what, phi d phi. It is not complete flux, we are going to find only a small part of it. That's why d phi is equal to E bar dot ds bar we are writing. Okay, so I want to find the total flux through this entire curved path, means I have to go to integrate it. Okay, so if I take it integration on both sides, the total flux we can write integral d phi equal to integral E bar dot ds bar. Therefore total flux through curved surface equal to phi is equals to integral E bar dot ds bar. So this is the formula, we have to take it. When we can take this integral formula, means either the flux is non-uniform or else the surface is curved. Here surface curved we took and we discussed this result. Okay, so flux means either you can write a scalar product of electric field intensity vector and area vector if the surface is plane. If the surface is curved, we can use this formula. Okay, next we can go for the next concept that is important for the board as well as objective also, that is the concept of electric dipole. Electric dipole. Here electric dipole, you observe dipole, di in the sense two, pole in the sense two pole, different polarities, means a system. Okay, if a system is there which is having two charges separated by certain distance, a system of two charges means equal and unlike charges separated by certain small distance is called electric dipole. A system of what, two equal in magnitude, unlike in charge. Two equal unlike charges two equal unlike charges separated by small distance, is called dipole. Suppose if this is a charge minus q and this is the charge plus q, and if these two charges are separated by certain distance, this is, we can call it as a dipole. So usually this is like if you take as a A and if you take as a B, the separation between them we take it as a 2A. You may have raised doubt. So here A we can take it now. Why you took here 2A? 2A in the sense, so dipole, if you want to find the field of this dipole, we should not measure the distance either from A or B. We will be measuring from the center of the dipole. When you are measuring from the center of the dipole, if you take totally A means from center to the charge is A by 2. That A by 2, if it is there fractional, while calculating, so complications will be arises. That's why to simplify, to avoid that complication, what we are going to take is 2A. 2A in the sense, you can understand that the distance of positive charge from the center is A. The same way the distance of negative charge from the center is A. So this is the thing. Next we can say, so understand here the two small charges separated by certain distance is called, the system is called as the electric dipole. Usually H2O, HCl, ammonia, these kind of molecules are behaves as a electric dipole. So their center of positive charge and a center of negative charge is separated by certain distance. They acts as a electric dipoles. Now we can go for next one. Important one is so the electric dipole moment. So what is electric dipole? You understood now. Electric dipole moment. So electric dipole moment is a vector quantity. So we will represent with P bar. So P bar is nothing but magnitude of either of the charge, because both are having same charge, that's why magnitude of either of charge into the displacement vector from what, A to B. So displacement vector from A to B means from negative charge to positive charge. That is, we will write as a Q into 2A bar. This is P bar. So usually we can take magnitude. If you have taken magnitude of P is Q into 2A, and the direction of this dipole moment, that is from negative charge to positive charge. So that's why we took here the displacement vector from A to B in the sense that is from negative charge to positive charge. So its direction is from minus Q to plus Q, and its magnitude is Q into distance between the charges. And you can write its units also. So its units are what? Charge is coulomb and distance is meter. So units of P is coulomb meter. This is the unit. Next we can go for the electric field intensity due to this dipole. So already we discussed the electric field intensity due to an isolated charge, that is E equal to 1 upon 4 pi epsilon naught into Q by R square. The previous videos you can check, go through it, you can understand. That is electric field intensity due to a isolated charge is what we are discussed, that 1 upon 4 pi epsilon into Q by R square. Here system of two equal and opposite charges. Due to these two charges, electric field intensity we need to be determine it. So in what way we can determine here is along its axis we can determine, means the line joining the two charges, that is we can call it as a axial line, and a plane which is perpendicular to the what dipole axis and passing through its center. So in that, on that plane also we can find the electric field intensity due to these two charges. That line is called equatorial line. So here the next we are going to discuss the electric field intensity due to dipole along its axial line, along its equatorial line. These are the very important derivations for the board concern, and 5 marks they will ask you, or else single is there. On one time they ask you for 3 marks. Very, very important. Follow it clearly. So next we are going to discuss that thing, electric field intensity due to what? Electric field intensity along the axial line of a dipole. See, along the axial line. So first you have to understand, dipole means you would know already. Axial line means the line which is passing through both the charges, that is called as the axial line. Now I am taking the thing here like this. So I have a dipole whose charges are minus q and here plus q, and the line which is joining these two charges is called as the what? Axial line, and the center to the negative charge distance is A, center to the positive charge distance is A. So what will happen here? These two charges we have, because of these two charges there we have a electric field intensity will be arises. So due to these two charges at a certain distance from this center O, this is let it be A and B, we consider a point P on this axial line. So axial line means you understand now, here the line which is passing through joining the two charges is called as the axial line. On this axial line we let it assume that is this as a point P. Okay, this point P, it is at a distance R from the what? Center of the dipole. So at this point P, electric field intensity due to these two we need to be determine it. Clearly understand now. First, due to positive charge, electric field intensity is away from it. Due to negative charge, electric field intensity is towards it. So this is electric positive charge. Due to this positive charge, here electric field intensity is away from it. So here that is electric field intensity to positive charges away from it, and due to this negative charge, here electric field intensity is towards it. So this is E minus Q. So to determine it, we need to find the what distances of these two charges, okay, from point P. So already it is R and it is A. So the remaining distance is R minus A. Means from positive charge to the point P, the distance is R minus A. So this is the distance R minus A. And as well as from negative charge to point P is totally you can say this is R, and additionally what is there totally from here to here it is R, and this part additionally it is there A. So R plus A. So from negative charge to here the distance is R plus A. Now we have to find the electric field intensity due to positive charge at point P. So electric field intensity electric field intensity at P due to plus positive charge, that is E plus Q equal to, we have the expression for electric field intensity due to isolated charge is 1 upon 4 pi epsilon naught into Q by distance square. So you can write 1 upon 4 pi epsilon naught into charge, magnitude of the charge Q by distance. Distance between what? Here BP. BP in the sense what is there? That is BP in the sense R minus A. So you can write as a R minus A whole square, because from positive charge to point A distance is R minus A. So the distance square we took here. It is away from the charge. It is direction is away from the charge. We can write. In the same way, this you take as a equation 1. The same way, the electric field intensity at point P due to negative charge Q is, so E due to minus Q charge at point P. That is E minus Q equal to, same we are following, that is 1 upon 4 pi epsilon naught into Q by, what is the distance from negative charge to the point P, means that is what? R plus A whole. So R plus A whole square. So this is towards the charge. So towards the charge we can write. Towards the charge direction. And this is equation 2. You observe these, they are opposite in direction. Here magnitude of EQ is more than magnitude of E minus Q. Why? Here in the denominator R minus A is there. Here denominator R plus A is there. Means here denominator quantity is smaller in magnitude. So E plus Q is more than the E minus Q. Why? Because here R plus A is there, here R minus A is denominator which is having less, this one is less. So denominator, if it is having less quantity, obviously its magnitude is more. Therefore we can write magnitude of E plus Q is greater than the magnitude of E minus Q. Therefore the resultant at this point is, so if two vectors are opposite to each other, its resultant will be what? Along the higher magnitude side. So this is the resultant direction. This is because E plus Q is higher magnitude. So along the higher magnitude side, that is E plus Q minus E minus Q. Therefore resultant electric field intensity at point P is E resultant equal to E plus Q minus E minus Q. Then if you substitute those expressions here, 1 upon 4 pi epsilon naught into, for these two 1 upon 4 pi epsilon naught common, and Q also I took common. In the bracket what is there? Here E plus Q in the sense 1 by R minus A whole square minus 1 by R plus A whole square. Then later we can write here common. The LCM is R minus A into R plus A, that is A plus B into A minus B means A square minus B square, like that. Here R square minus A square whole square, and ER equal to Q by 4 pi epsilon naught into, here LCM is R square minus A square, R square minus A square whole square. Okay, and then the numerator R plus A whole square minus R minus A whole square, you will get it. Then finally here like A plus B whole square minus A minus B whole square means 4AB. Like that, here you can write Q by 4 pi epsilon naught into 4AB, 4 into R into A. So 4AR by R square minus A square whole square. This is the thing, you will get it. Now this can be simplified like this. So 1 upon 4 pi epsilon naught into, we have the result like this, E resultant equal to 1 upon 4 pi epsilon naught into Q into 4AR by R square minus A square whole square. So this is a small rearrangement I will do. here 1 upon 4 pi epsilon naught. So Q into 2A I will write together. So still we have 2 because it has 4. Already here we used 2. Still we have 2 into R by R square minus A square whole square. Already we discussed the product of charge and distance between the charges is dipole moment. Then we can write 1 upon 4 pi epsilon naught into 2pr by r square minus a square whole square. Since p means since p equal to q into 2a. This is already we discussed dipole moment. This is the electric field intensity along the axial line due to a normal size dipole. If the dipole is very short, means small dipole we have. If a very small dipole is there, the distance of the point P is very large. So we can take the condition in case of short dipole, means very small dipole is taken, compared to the dipole distance, R is very large. So dipole is very small, the point is R is very large. So this is A, this is R. So R is very much greater than A is possible. That is in case of short dipole. So in case of short dipole we can write that R is greater than A. So R square is very much greater than A square. Therefore A square can be neglected. If A square if neglected, this equation now going to be changed. Therefore the resultant electric field intensity is 1 upon 4 pi epsilon naught into 2pr by, if you A square if you neglected, r square whole square will be there. That's why it is r power 4. Therefore er equal to what? 1 upon 4 pi epsilon naught into 2p by r cube. Its direction how it is there? Away from the positive charge. So or else you can write as along the dipole moment. So along the dipole moment. So this is the thing we can take it from axial line, electric field intensity along the axial line. So next